Hello, everybody. This is Gustavo, exam coach. Today, I'm bringing you a lesson about inequalities, a fundamental topic in your preparation for the GMAT quantitative section. Let's begin. Inequalities are a lot similar to equations. There is a number of rules that you use in order to solve equations. And we can say that the principles by which we solve, for example, um, one variable equation is what we call the reduction of like terms. In inequalities, it's pretty much the same thing, but there are some restrictions that you need to keep in mind when operating and solving inequalities. We'll deal with these restrictions in a way or under the guise of properties. Okay, so let's talk about our property number one or restriction number one. When working with variables in inequalities, you need to know the sign of the variable when multiplying or dividing both sides. Otherwise, you will have to operate assuming both scenarios, positive and negative. Say, for example, I want to simplify this equation, right? Let's say that we have a times x equals b times x. Okay, provided that x is different from 0, right? We could just simplify this and this because we would say, okay, I can divide both sides of this equation by the same factor x. In that way, I'm guaranteeing the cancellation of the factor. All right, you do this disregarding the sign of the factor x. But in inequalities, if you had something like this, for example, you cannot just cancel by saying I'm dividing by x, so x will be canceled in the end. You need to consider that when you divide by a positive factor both sides of an inequality, all right, the effect is that the factor will go away and you will be left with this simplified inequality. But if the factor you intend to cancel has a negative sign or represents a negative numerical value, then you need to remember that at the end of the operation, the direction or the sense of the inequality symbol need to be reversed. Okay, so for example here, I know x is negative, I will divide by x both sides of this inequality, but in the end, I will get this. X will go away, will be canceled, but then I will be left with inequality a is greater than b. All right, otherwise we will get accuracy problems with our results for the inequality we are trying to solve. Same thing happens when you multiply both sides of an inequality with the same factor. Say, for example, here, if I want to move one factor in one of the sides of an inequality, for example, x, I want to move x to the other side. Okay, typically you say x is dividing on the left side. I will move it to the right side, multiplying the other side, the right side. All right, this will eventually result, is expected to result in something like this. Okay, although this might be true when x is simply a positive number or represents a positive number, when x represents a negative value, you need to consider that the inequality symbol will be reversed. Why? What is going on here is that you're actually multiplying both sides of this inequality, multiplying by the same factor x. So what results is that the x becomes canceled on the left side, but it appears on the right side of the inequality, multiplying whatever terms are there. And If it was initially less than the direction of the inequality, then you need to reverse it to greater than. So you will get something like this. All right, every time you are tempted to cancel one factor because it's easier, because it will make the inequality look simpler. All right, be careful about this. This consideration you needn't take when adding or subtracting the same term on both sides of an inequality. The sign doesn't matter. You can do this disregarding the sign of the common term you're adding or subtracting. The inequality symbol, whatever it was originally, will never change its direction or its sense. Let's move on to the second property of inequalities. You can add two inequalities if they have the same inequality symbol. You cannot subtract inequalities, and you can do this regardless of the sign of the variables. Let's say that we have two true inequalities such as A is less than B and C is less than D, where A, B, C, and D all represent different algebraic expressions. Based on these true inequalities, we can conclude a third true inequality that is obtained by adding the left sides of the inequalities and the right sides of these inequalities correspondingly. So we would have that A plus C must be less than B plus D. But there's no way from these two true inequalities to obtain anything in general about this difference and regarding to this other difference. We cannot conclude what is the relationship between the two differences in order, because we would have to know the particular values of each of the expressions in this inequality. There's no way to generalize, which is another way to say you cannot subtract inequalities. All right. This actually could be any possibility. It could be greater than, less than, or even equal to, provided that the appropriate values appear on these algebraic expressions. Let's try an inequality property number 3. The product of two inequalities can be found between two end values, the least and the greatest product of the upper limits and lower limits for each of the algebraic expressions or variables, right, in each inequality. Consider, for example, a double inequality, x is greater than -6 and at the same time less than 7. And then you have another double inequality, y is greater than -5 and less than 8. What we're saying with this property is that if you need to find the upper and lower limits for the product of these two algebraic expressions, all right, you will find the minimum and the maximum thresholds by attempting all possible products between the upper limits and the lower limits. So there are two possible or four possible products actually that you can try. As you can see here, among the items on this list, you will have to choose the true minimum value. Actually, 30 is the true minimum value, and no, it's not. 30 is just a positive minimum value, but there is one that it's even lower than that. -48 is the true minimum value for the product, and the true maximum is actually 56. So that's it. The product of these two can be found. The product of x and y, it is limited by -48 and 56 positive. Of course, this rule can be simplified a little bit if you are trying to combine two double inequalities where the upper and lower limits and each inequality are just positive numbers. Example, let's say that I have t is between 5 and 2, and I have w is between 1/2 and 1/3. So what about the product of these two? Would be enough to say that WT is greater than 2/3 the product of these two, and the how to say, upper limit is 5 times 1/2. Okay, take a look. 5 over 2 is 2.5, and 2/3 is less than 1. This is actually the correct boundaries for the product of W times T. How about the negative and positive values? Okay, if that's the case, you just do as in the example above. Let's try property number 4. It says the ratio or product of two variables or algebraic expressions in general greater than or less than 0 only gives you information about the sign of the variables. Take a look at this. You have a ratio of two variables, here a product, but if either the ratio or the product is greater than 0, then you know that x and y must have the same sign. Two positive or both of them negative. But if they tell you that the ratio or the product is less than 0, then you know that the two expressions appearing in the ratio or the product are actually different in signs. But if you don't know the sign of any of them, you need to consider both possibilities in your analysis. Now, there are some variations that are very commonplace in the GMAT, and especially this one is very commonplace when they tell you that the ratio of two variables is greater than 1. Although this might look similar to x over y is greater than 0 because actually 1 is positive, so it's greater than 0, the ratio. If the ratio is greater than 1, it is not the same thing. It doesn't simply mean that x and y may have the same positive sign or the same negative sign. It means something else. Let's see. Imagine that you assume that they are both positive. X and y are positive. Okay, what would happen if I multiplied both sides of this inequality by y, which is a positive number? Then I would have this, x is greater than y. On the other hand, if I assume that x and y are both negative, then if I multiplied both sides of the inequality by y, which represents a negative value, the direction of the inequality symbol would have to be inverted or reversed, right? Resulting in something like this. X is less than y. So what the inequality x over y is greater than 1 actually means is either of these two cases. Either the two are positive, but they are in this specific order, or the two are negative, but they are in this specific order. So this is what the inequality x over y greater than 1 actually represents. Let us deal with property number 5. When you take the reciprocal of an inequality, the inequality sign changes. You can only take the reciprocal if all of the variables have the same sign. What this means is if you have a relationship of order among several numbers, and you can represent this with an inequality such as this, and you know that all the numbers or variables or algebraic expressions in general have all the same sign. They are all positive or they are all negative. Then what you can be sure about is that the reverses or the inverse or reciprocal of these expressions, A, B, and C, will always appear in the inverse order. All right, so let's see several examples. Example number one. Let's say that you know that x is a number greater than y, than 5, sorry. So if x is greater than 5, then as 5 and x represent both positive numbers, you may immediately conclude that 1 over x has to be less than 1 over 5. The inverse of x should be the same as the, or be less than the inverse of 5. But if you know that x is positive, the inverse of a real number or its reciprocal will never have a different sign. If x is positive, the inverse of x is also positive, and vice versa. If x is negative, the inverse of x will also be negative. So remember that although we're saying that 1 over x is less than 1 over 5, 1 over x is still positive. Okay? Be careful about that. Now, what about another example? We are saying that, for example, if you have that 1 over y, right, is a negative number less than -2. So from this inequality, it is clearly noticeable that -2 represents a negative number. 1 over y being a number less than -2 must be negative as well. So what about the inverse of 1 over y? That would be, right? If you invert this, you would have y, and the inverse of -2 would be -1 over 2. And the relationship would change. Y would be greater than -1/2. But remember, if 1 over y was negative in the first place, then the reciprocal of 1 over y, that is y, should be also negative. So let us not forget that y is a negative number still, although greater than -1/2 should be negative. So this represents the correct relationship between y and its boundaries. Let's see another example. If they tell you that z, for example, is a number greater than -1/3. All right. You can see that on the right side of this inequality, you have a negative number. But on the left side, actually, z represents any number greater than -1/3. But greater than -1/3 could be negative or 0 or even positive, right? So here you cannot just say, okay, you cannot just say that, because z is greater than -1/3, I can say that 1 over z, the reciprocal of z, is less than -3. This is partially true. Why? It only applies if z is a negative number. If z is a negative number, then you can say that the reciprocal of z is less than -3. Okay? But what if z takes positive values? Because if it is greater than -1/3, it might also be positive. So if it is positive, then 1 over z, the reciprocal, would be also positive. So you have two cases to take care of. Okay, be careful about this. Actually, when the two sides of an inequality do not represent numbers with the same sign, then you need to be careful. There's only a partial application of this property 5. Finally, we'll see another property, which is actually a nice template to help you solve out quadratic inequalities with one variable on the spot. Let's give you a little context here. You have the general quadratic equation with a single variable of the form ax squared plus b times x plus c equals 0. We know that if we solve a general equation like this, we would obtain, generally speaking, two solutions, x1 and x2, two roots of the equation. Let's assume just to make our presentation easier to understand that the first root is less than the second root. Let's call x1 the least of the two roots. So, what can we learn from these results? If I want to solve an inequality of the form ax squared plus bx plus c is greater than 0, you can directly generate the solution set for all possible values of x that satisfy the inequality. Once you find the roots x1 and x2 corresponding to the quadratic equation, in which quadratic equation? The one that would result from substituting the inequality symbol for the equality symbol. Okay, once you solve x1 and x2, then you can say the solution set for this inequality, ax squared plus bx plus c is greater than 0, would be simply all values of x that are outside the interval formed by the two roots of the equation. In other words, x less than x1 or x greater than x2. All values of x outside the interval formed by the two roots of the equation will be solutions to this inequality. On the other hand, if you have the inequality ax squared plus bx plus c is less than 0, then you can say that the solution set for this inequality would be this double inequality, all possible values between the two roots of the corresponding equation. Okay? This is a rule, like a template you can apply to solve faster quadratic inequalities, right? Provided that in all cases, A is a coefficient greater than 0. Be careful, be mindful. The coefficient of the quadratic term must be positive for this to be true. Otherwise, if the coefficient A is not positive, you can just multiply both sides of the inequality by -1, turning in this way the sign of coefficient A to positive. Okay, let's see an example. If I have quadratic inequality, x squared minus 5x plus 6 is greater than 0, then if I solve the corresponding equation, this one, I would have two roots or solutions. Since here you have 1 as the coefficient of the quadratic term and it is positive, then checking that the inequality symbol is greater than, we would have to apply this pattern, right? So I just enunciate the solution set for the inequality. Two intervals of values for x. values of x that are less than positive 2, or which is, 2, positive 2 is the list of the roots of the equation, or values of x that are greater than the second root. And this would be our solution set. Okay, these are all the properties of inequalities you need to master. Actually means you need to realize how to apply this, and of course you need to memorize them.